Well, hello and welcome. This is like some linear algebra notes that we're going to make. I recognize the situation is like perhaps less than ideal because, I mean, the video is probably not going to be the best, but it is what it is, and like hopefully we can make some sense out of this stuff. So what we're going to talk about to start with is this idea of a determinant, and that's sort of like what the whole unit is about that I'm just not going to be here for. So I think ideally maybe in pre-calculus or wherever else we started to get exposed to matrices, we understand the idea of a determinant, particularly in the case of like a 2 by 2, right? We would just do like, well, it's A, D minus B, C. And if it was like a 3 by 3, like we have A, B, C, D, E, F, G, H, I. And then, well, what we would do is A, D, G, B, E, H. And then we would do some like thing where you did like the diagonal parts, except for it's not drawn great. And then you would do like this thing and this thing and this thing. I don't honestly, I don't really remember it that well, but like that's what we understood about determinants, and we calculated it pretty well, and I don't know, that's what that was. Primarily because, well, this is a class where we ask questions for like where does it come from? Why is it useful? Those are the questions that we're going to explore when it comes to determinants. Are we going to need to calculate them all the time? Not necessarily. You know, we have programs like MATLAB or computers that can calculate determinants, so we're not necessarily interested in calculating them. But what we are interested in is the question like, why are they a thing? What do they tell us about a matrix? And like, why does it work? And so we're going to generalize determinants to like n by n matrices, right? It could work for not just 2 by 2 or 3 by 3. Maybe some of you have done this idea of cofactor expansion, which is where you had like minor matrices and you would do like a plus minus plus rule or something. Hopefully what we can do is sort of like take that idea, fill in the gaps, and then generalize it. And what we're going to talk about in this first video is not necessarily like how to do it, or like we're just going to kind of motivate the idea of a determinant, and we're going to motivate it through a bundle of vectors. So let's just say I have like some collection of vectors, right? There'd be i's, and I have like 1 to n, and they're all in Rn. One of the things I want you to notice is that like I have n vectors in my bundle, right? And it's also Rn. So the number of vectors that I have is also the number of vectors, is also the dimension of my space. N vectors, n-dimensional space. And what I want to talk about is this idea of like a parallelepiped, which is a very weird thing, but actually I've got a picture of it right here. If you think about it like, okay, so any collection of vectors is going to define a sort of generalized parallelogram. Okay, so if I had two vectors in R2, right, maybe one of them looks like this and one of them looks like that. This will be like vector 1 and vector 2. Well, if I take vector 1 and like also put it at the end of vector 2, so this is like another version of vector 1, and I drew it a little bit too long, and then I take vector 2 and make like another version of vector 2, it actually makes a parallelogram, right? Because they're like, well, they have to close up onto each other, and so it encloses a shape in two-dimensional space. So this is two vectors, and they enclose a shape in two-dimensional space. Over here in this diagram, right, like I have three vectors, and they're enclosing a shape in three-dimensional space. So like A is also projected over here. This vector is also A. This vector is also A. This vector is also A, right? And then, well, I've got a couple of C's out here, so like C ended up coming over here, and coming over here, and coming over here, so these are all C vectors. And then B obviously does the same thing. So all of the edges of this shape are the vectors that are in my bundle, and I have sort of like copied and pasted them in enough times to enclose a shape. And well, that shape is called a parallelepiped, which is like P-A-R-A-L-L-E-P-I-P-E-D. And it's sort of this like generalized version of a parallelogram, right? And the question that we're going to sort of ask ourselves is like, well, what is the volume? And I'm going to put volume in quotes, because when we use the term volume, it's going to depend on the kind of space that we're talking about. But the idea is that, like, well, what is the volume of this thing? The parallelepiped. And the idea is that, like, well, in one dimension, it's just the length of your one vector, right? If you only have one vector in this bundle and it's in R1, the sort of like volume in one dimension is just length, right? It's the idea of scale in the only dimension that you have, and that's length. If you have like two-dimensional space, the sort of volume that we're talking about of a parallelepiped, which looks like this, sort of volume is the scale in two dimensions, which we call area, right? And then obviously in sort of like three dimensions, we have this idea of like, he goes up there, and then, well, then there's another one, and another one. Well, he would go out this way. I don't know, man. We have like then this is volume, is actually volume. And in n-dimensional space, if I had like a 15 vectors, it would make, well, a 15-dimensional shape, and we would just have like the volume of a 15-dimensional parallelepiped, all right? And if I take this collector, what does this have to do with determinants? Well, I'll tell you. So if I take this collection of vectors and we smoosh them together again to make a matrix, which we'll say A, right? So A has like V1 is the first column, V2 is the second column, and then I have all the way out here Vn, okay? I'm going to say that, like, well, we're going to figure out sort of like the determinant of matrix A is really going to be the same thing as the determinant, which we'll just call capital D, of like this collection of vectors V1, V2, all the way to Vn. And then, like, well, you know, I could sort of expand this out if I wanted to. A11, A12, all the way out to A1n. Now, these matrices are always going to be a square, right? When we talk about determinants, you have to talk about square matrices, because, again, I said the number of matrices in my bundle is exactly the number of dimensions. So these vectors are all going to be n tall, and there will be n of them. So down here I have an1, an2, and then like down here at the bottom I have ann. So we would sort of like the determinant of this thing. You guys have probably seen it before. It's like matrices, but you just do a vertical bar. So you've got A11, A12, A1n. Down here I've got ANN, here's like AN1, AN2. So this is how we sort of like write determinants. This is how determinants have to do with like a bundle of vectors instead of an actual matrix. And the question we're sort of going to explore in the next video is this idea of like, what is the volume of this parallelepiped that I could make out of all of these vectors, the vectors that I've sort of smooshed together in my matrix. So we'll take a second to digest, and then we'll start the next video where we explore this question.